Okay, let's dive right into this. We're going to break down the actual science behind a plumbing system that works. Taking it from the complex rules you see in a code book to what actually needs to happen on a construction site. It's all about turning that theory into reliable pipes.
It's a question that drives homeowners and engineers absolutely crazy. You've got brand new pipes, new fixtures, everything looks perfect. So why are you still dealing with clogs or leaks or even worse? Well, the answer, as we're about to see, has nothing to do with bad luck. It has everything to do with physics.
And that's really the whole point, right there. A plumbing system that actually lasts isn't just thrown together, it is engineered. You can have a total mess that's born from guesswork, or you can have an efficient, ordered system where every single part is chosen because of hard numbers. So, here's our game plan. We'll kick things off with the foundational math, the design basis. Then, we're going to follow the water's path through the supply network and the drainage network. We'll also cover the absolutely critical safety systems that prevent disasters, and then finally, we'll tie it all together to show how these equations become a flawless system.
All right, first things first. Before you even think about cutting a single pipe, you have to establish the design basis. This is where we stop guessing and start engineering. This is how we make sure the entire system is built on a solid foundation of calculation. And now don't let this table intimidate you. It's basically the entire language of plumbing design. Let's just quickly run through it. For water supply, Q is your flow rate, and you get that using fixture units, or FU. That's just a number assigned to every faucet or toilet to figure out the total demand. For drainage, velocity is everything. It's got to be fast enough to carry waste away. For pressure, P equals rho GH, density times gravity times height, which tells us how much force that water is pushing with. Look, these aren't just random equations. They are the tools that separate a professional, calculated system from just, amateur guesswork.
Okay, with our foundation set, let's move on to section 2. Now we're looking at the supply network. This is the side of the system that's under pressure, delivering clean water exactly where you need it, when you need it.
So what even is pressure? Well, it's just the weight of water pushing down. The equation P equals rho GH shows it perfectly. Pressure is just the density of water times gravity times the height of the water column. A really simple rule of thumb is this. For every 10 meters you go down, the pressure goes up by about 1 bar. So if you've got a 40-meter building like this one, you're looking at almost 4 bars of pressure at the bottom, just from gravity doing its thing.
Now all that pressure has to be contained, and that brings us to materials. You'll usually see PPR pipe for both hot and cold water because it can handle the heat. PVC, on the other hand, is only for cold water and drainage. A classic interview question is, so why can't you use PVC for hot water? And the answer is simple. It deforms, it cracks, it fails. It's such a common mistake to try and cut costs this way, and it always leads to catastrophic leaks. See, the material choice isn't just a preference, it's a direct result of physics.
So what if the pressure coming into your building is just too high? Well, the building codes say anything over about 5.5 bar is a problem. The solution is a pressure-reducing valve, or PRV. But here's the mistake you see all the time on job sites. Installing it is only half the battle. If you just walk away without actually setting and calibrating the downstream pressure, that valve is basically doing nothing, and you're still going to damage every fixture connected to it.
All right, we've successfully brought pressurized water in. Now we have to get the wastewater out. Let's switch gears to the drainage network. This side of the system, it's not about high pressure. It's about a really delicate but crucial balance between gravity and air.
This little U-bend, this is the P-trap. It's one of the simplest and honestly most brilliant inventions in plumbing. It just holds a little plug of water that physically blocks nasty, smelly sewer gases from coming up your drain. But a really common and dangerous mistake is installing an S-trap instead. The shape of an S-trap can create a full siphon, and it will suck that protective water seal right out, leaving an open highway for toxic gas to get into the building.
Okay, so that leads to the next logical question, right? Even with a proper P-trap, when a big rush of water goes down the drain, it creates negative pressure behind it. And that pressure change threatens to suck that protective water seal away. So, what protects the protector?
And the answer is the vent pipe. I've loved this illustration. Think of it as the plumbing system's lung. When a slug of water rushes down that drain pipe, the vent lets air get pulled in from behind it. That neutralizes the negative pressure, and it protects the P-trap's water seal. The code is crystal clear on this. The vent pipe's diameter has to be at least half the diameter of the drain it's serving. This is not optional, it is essential.
And to really hammer this point home, here's another one of those classic interview questions. What happens if you just skip the vent in a multi-story building? Well, the rush of water from a toilet on an upper floor will create a powerful vacuum, and it will siphon the P-traps on every single floor below it. One little omission, one shortcut, can lead to a catastrophic failure that fills the entire building with sewer gas. Okay, now let's talk about the slope of those drain pipes. You might think, oh, steeper is better, right? But it's not that simple. This is what I call the Goldilocks principle of drainage. As this chart shows, if the slope is too shallow, the velocity is too slow, we're talking less than 0.6 meters per second, and solids get left behind. That's a clog waiting to happen. But if the slope is too steep, the water actually outruns the solids, leaving them stranded and causing a blockage anyway. You're always aiming for that sweet spot, that green self-cleaning zone right in the middle.
So, the system is designed for perfect flow. But what happens when things go wrong? This section is all about those critical safety components that are our last line of defense against contamination and, well, total system failure.
One of the most dangerous failures you can have is something called backflow. This is when contaminated water, say from an irrigation system or some industrial process, flows backward into the clean water supply lines. It happens under one simple condition: when the pressure downstream on the dirty side becomes greater than the supply pressure upstream. And that can introduce serious health hazards right into your drinking water. So how do we stop it? Well, the main defense is a backflow preventer, a special valve that just stops that reversal. Then, for maintenance, the code demands cleanouts. These are what give us access to clear any blockages. And their placement isn't just random. The International Plumbing Code, the IPC, is very specific about where they go: at the start of every horizontal line, every 15 meters on straight runs, and after any significant turn. This isn't just about safety, it's about designing a system that you can actually maintain for years to come.
Okay, let's bring it all together now. We've looked at the formulas, we've looked at the components by themselves. Now let's really reinforce that direct line between what you calculate on paper and how those pipes actually perform once they're sealed up inside a wall.
If you remember just one number from our whole discussion on drainage, make it this one: 0.6 meters per second. This isn't some arbitrary target, it is the absolute minimum velocity you need to create a self-scouring flow that actually carries solids away. Anything less than that, and you're not just installing a pipe, you're designing a future blockage. It's that simple.
And that brings us to the most important takeaway of all. The plumbing code isn't just some big book of arbitrary rules they made up, it's basically a physics textbook in disguise. The requirement for a vent pipe, that's about atmospheric pressure. The rules for slope, that's fluid dynamics. The specifications for materials, that's thermodynamics. It all comes back to science and numbers.
So I'll leave you with a final thought to really connect all the dots. Imagine you've calculated the absolute perfect slope for a self-cleaning flow, making sure the velocity is just right. Why can that perfectly sloped pipe still clog up and fail if its vent is undersized? It's because no single component in the system works in isolation. Because in the end, success comes from seeing plumbing not as just a collection of parts, but as a complete, interconnected system. When you design with the code, when you calculate with purpose, and when you truly understand the physics behind every single connection, that's when